Signals and systems, correlation, series on signals and systems, lecture number 1.22. Correlation refers to a measure of similarity between two different signals or a signal and its shifted version. In the first instance, it is called cross correlation, and in the case of second instance, it is called autocorrelation. Mathematically, correlation involves a set of mathematical operations between the signals, like the operations in convolution. In fact, correlation and convolution, these two are highly related. Correlation's importance mainly lies in the fact that it is widely used in communication systems, especially radar communication systems. Here in the present session, we understand in depth about correlation, first by considering the definition and then their properties and then their applications. Let us move further to start the session. Cross correlation. Cross correlation between two signals gives a measure of similarity between them as function of a parameter known as searching or scanning parameter tau. As already mentioned, cross correlation refers to similarity between two different signals, whereas autocorrelation refers to similarity between a signal and its shifted version. In case of cross correlation, the similarity is available. Similarity between two different signals, it is available as a function of a parameter. This parameter is known as searching or scanning parameter. Usually it is indicated by tau. It can be seen correlation is a time domain parameter, a time domain operation, or a time domain process manipulation, whereas its corresponding frequency domain operation is filtering. So correlation in time domain corresponds to filtering in frequency domain. The cross correlation function of signals f1 of t and f2 of t can be shown as the response of the system with the impulse response f2 of minus t when driving function is f1 of t. So this particular relation has to be kept in mind because it has certain special significance, and also we come across this particular relation several times in the study of correlation. Now we consider correlation between non-periodic signals. First cross correlation and then autocorrelation. Correlation is indicated by symbol phi. Phi 1, 2 of tau. 1 refers to function f1, 2 refers to function f2. Cross correlation between two functions f1, f2. It is indicated by phi 1, 2. By definition, it is integral minus infinity to plus infinity f1 of t, f2 of t minus tau dt. It is equal to integral minus infinity to plus infinity f1 t plus tau f2 of t dt. This is the case when the signals are real. When the signals are complex, then cross correlation between the functions f1 and f2 It is by definition integral minus infinity to plus infinity f1 of t conjugate of f2 of t minus tau dt. Of course, this is equal to integral minus infinity to plus infinity f1 of t plus tau multiplied by conjugate of f2 of t dt. So here we have defining relations of cross correlation in case of non-periodic signals for CT case, CT domain signals. Now autocorrelation. Phi 11 tau correlation between signal and its shifted version. Phi 11 of tau is integral minus infinity to plus infinity f1 of t multiplied by f1 of t minus tau dt. It can be shown equal to integral minus infinity to plus infinity f1 of t plus tau multiplied by f1 of t dt. This is in case of real signals. In case of complex signals, it is integral minus infinity to plus infinity f1 of t multiplied by conjugate of f1 of t minus tau dt can be shown equal to integral minus infinity to plus infinity f1 of t plus tau multiplied by conjugate of f1 of t dt. This is for complex signals. So cross correlation, autocorrelation, real signals, complex signals. All the situations are dealt. Of course, for the case of non-periodic signals. Now we consider correlation between periodic signals. Cross correlation between periodic signals. Phi 12 tilde of tau is 1 by t, this time period. Integral minus t by 2 to t by 2. f1 of t multiplied by f2 of t minus tau dt. It can be shown equal to 1 by t integral minus t by 2 to t by 2 f1 of t plus tau multiplied by f2 of t dt. Autocorrelation. Autocorrelation between two periodic signals. It is indicated by phi tilde 11 of tau equal to 1 by t integral minus t by 2 to t by 2 f1 of t multiplied by f1 t minus tau dt equal to 1 by t integral minus t by 2 to t by 2 f1 of t plus tau multiplied by f1 of t dt. So this is the slide containing definition of correlation for periodic signals. Earlier definitions are given for non-periodic signals. Correlation and convolution, these two are highly, heavily, greatly, closely related. That relation is explained, described, given in the present slide. Correlation versus convolution. Correlation is similar to convolution in every aspect except that folding back about the vertical axis is not done. So if one of the functions is even, the cross correlation and convolution, they become equivalent. So in correlation, folding back about the vertical axis that exists in convolution, it doesn't exist in correlation. Okay. Once we have this particular connection in our minds, we can notice phi 12 of t, cross correlation between f1 and f2. It is equal to correlation between f1 of t and f2 of minus t with t equal to tau. Similarly, cross correlation between 2 and 1, phi 2 1 of tau is equal to f2 of t convolution with f1 of minus t with t equal to tau. Autocorrelation phi 1 1 of tau is equal to correlation between f1 of t with f1 of minus t with t equal to tau. These three relations give good amount of information between correlation and convolution. Now we spend some time on properties of cross correlation. Phi 1 2 of tau, that is cross correlation between 1 and 2. It is equal to phi 2 1 of minus tau. That is cross correlation between 1 and 2 is equal to cross correlation between 2 and 1 with minus tau in place of tau. Another property, phi 1 1 of 0 plus phi 2 2 of 0. This is one autocorrelation. This is another autocorrelation. First one refers to autocorrelation of F1. Second refers to autocorrelation of F2, both at tau equal to 0. Sum of these two is more than twice mod phi 1 2 of tau. Another relation, Fourier transform of phi 1 2 of tau yields f1 omega multiplied by f2 of minus omega. It means cross correlation between two signals in time domain. It corresponds to multiplication in frequency domain. Of course, in f2, omega has to be replaced by minus omega. The same thing is mentioned here. Fourier transform of cross correlation function between 1 and 2 is product of f1 omega with f2 of minus omega. Now properties of autocorrelation. For a given function f of t, there is a unique autocorrelation function, but the reverse is not true. So autocorrelation function of a time domain function f of t is unique, but converse is not true. It implies one autocorrelation function may be autocorrelation function for several time domain signals. A given autocorrelation may correspond to an infinite variety of waveforms. The maximum value of autocorrelation function occurs at the origin. Its value becomes smaller for larger values of tau. Phi 1 1 of 0, it is more than modulus phi 1 1 of tau when tau not equal to 0. The value of the autocorrelation function at the origin is equal to energy of the signal. Phi 1 1 of 0 is integral minus infinity to plus infinity f1 square of t dt. Some more properties of autocorrelation function. The autocorrelation function is an even function of tau. That is phi 1 1 of tau is equal to phi 1 1 of minus tau. There is a theorem, autocorrelation theorem. What does it say? The Fourier transform of autocorrelation function phi 1 1 tau yields pi times the energy density function of f1 of t. That is Fourier transform of autocorrelation function phi 1 1 of tau is magnitude f1 of omega whole square. It is equal to pi times s1 of omega. Here note one aspect. Sometimes we are using one type of phi, and sometimes we are using some other symbol to denote phi, but essentially They are not different. They are to be considered the same. Some more properties of autocorrelation function. The average autocorrelation functions are periodic functions with a period same as that of correlating functions. The significance of this property lies in the fact that it enables us to detect periodic signals in the presence of noise by using correlation technique. We need to go through it. The average correlation function, or periodic functions with the period same as that of correlating function. Significance is it enables us to detect periodic signals in the presence of noise. Fourier transform of phi11 tilde of tau yields pi times the average power density P of omega. That is, Fourier transform of pi tilde 1 of tau is pi times power density function P of omega. Now the importance of correlation. Its importance is mainly due to its need, due to its necessity, due to its usage in detecting signals. Signal detection is carried out using the concept of correlation. These methods are based on the autocorrelation function of a periodic signal is also a periodic function of same frequency, and autocorrelation function of non-periodic function tends to 0 for large values of tau. It is possible to obtain the actual waveform of the periodic signal if the received signal f of t is cross-correlated with a periodic impulse function of frequency equal to that of the desired signal. So these are some of the things which I want to share with you in this session. Now we have come to the end of this present session. Before closing down, let us recollect the important aspects that are discussed or considered in the present session. Cross correlation has been introduced, the definition has been given. Autocorrelation has been introduced and a definition has been given. Cross correlation and autocorrelation for both non-periodic as well as periodic signal. Their definitions, their properties, their importance, their applications, they are all discussed in the present session. Hope this session is quite useful to you. We meet again in another session with a new topic soon.